You know, when we look up at the sun, it seems like this perfect, steady ball of light, right? But if you could get up close, you'd see it's this incredibly chaotic, churning world. And flowing right across its surface are these massive weather systems. I'm talking about currents of plasma larger than our entire planet. It's wild. So, what's really driving all that activity?
And that's not just a casual question. For decades, this has been a huge mystery in solar physics. We can see these enormous flows happening, but we've been scratching our heads trying to figure out what the engine behind them really is. What forces are so powerful that they can orchestrate weather on the scale of an entire star?
Okay, so let's meet the first of these giant systems. It's called the meridional flow. The best way to think about it is like a giant conveyor belt. In each half of the sun, you've got this flow that starts at the equator and moves up toward the poles, cruising along at about 35 miles per hour. Now, its big job is to drag the sun's magnetic fields along with it, which, as you can imagine, plays a huge part in the whole solar cycle.
And then there's the second system, the torsional oscillation. Now, if the first one was a conveyor belt, this one is much more like our jet streams here on Earth. These are basically bands of plasma that rotate a little bit faster or a little bit slower than everything around them. And these bands drift across the sun's surface over that famous 11 years solar cycle.
So you've got these two massive, distinct flow systems, and they both seem to dance to the rhythm of the 11-year solar cycle. And what's the most famous feature of that cycle? Sunspots, of course. So for years, the most logical assumption was that these super intense magnetic regions, the sunspots, were the main culprit, the things pushing and pulling these giant currents around. But here's the thing about science. An assumption is just an assumption until you can prove it. And how on earth could you test this? It's not like you can just fly up to the sun and switch off the sunspots to see what happens. Or can you? Well, a team of scientists came up with this incredibly clever method to do the next best thing. They figured out how to perform a kind of digital surgery on the sun. Here's how they did it. Using more than a decade of super high-resolution data from NASA's Solar Dynamics Observatory, they were able to pinpoint every single active region, every sunspot on the solar surface. They could map the very center of each one, which you see here as a green cross, and then draw these really precise zones around them.
The method itself is just beautiful in its simplicity. Step 1, map all the sunspots. Step 2, draw those exclusion zones around them. Step 3, and this is the genius part, they digitally erased all the flow data from inside those zones. And then, step 4, they analyzed what was left behind, what you could call the quiet sun, without all the noise from the sunspots.
All right, so let's put this incredible technique to the test. First up, the jet streams, that torsional oscillation. Now, if the theory is right, if sunspots are really driving this pattern, then when you digitally remove them, well, the pattern should get a lot weaker or maybe just vanish completely. So what do you think they found? So check this out. On the left is the torsional oscillation with all the data, sunspots and all. And on the right, that's what it looks like after the digital surgery. And, well, would you look at that? They're almost identical. The pattern is still there, clear as day, just as strong as it was before. The researchers pretty much said it all in their paper. The torsional oscillation is a global thing. Taking the sunspots out of the picture doesn't really affect it. The big takeaway here? Our prime suspect is innocent. Sunspots do not drive these solar jet streams. Okay, so one mystery down. But what about the other big one? That giant conveyor belt, the meridional flow. The old idea was that the powerful rush of plasma towards sunspots was what caused all the variations we see. So what happens when they apply the same digital surgery to this system? And this is where things get really dramatic. On the left, you see the meridional flow as we've always seen it. It's a chaotic mess, totally dominated by those powerful flows rushing into sunspots. But then look at the right. After the surgery, with all that sunspot noise just gone, a faint but incredibly clear global pattern suddenly appears. It was there all along. The surgery worked perfectly. It turns out the effect of the sunspots was so strong and so localized, it was acting like static on a radio, just completely drowning out a much weaker, more fundamental signal hiding underneath. By cutting out the static, they could finally hear the music. And what they heard led to a completely new way of thinking about this. The meridional flow isn't just one thing. It's actually a system with 3 different parts. First, there's a constant baseline conveyor belt that's always there. Second, you have those strong temporary inflows that get pulled towards sunspots. And third, there's this weak, hidden flow that changes globally with the solar cycle. And here it is. This is that hidden third part, finally unmasked. What you're looking at are these faint bands of flow. They start at the higher latitudes and then slowly drift toward the equator over several years. They're perfectly in sync with the solar cycle, but they're completely independent of the sunspots themselves. And get this, the speed of this hidden global flow is only about 2 meters per second. That's literally the speed of a brisk walk. A flow that slow, spread across the entire sun, was completely invisible to us until they figured out this brilliant way to surgically remove the much louder, much stronger signals from the sunspots. So the big takeaway is that our whole model has changed. We've gone from this simple idea of a conveyor belt that gets messed up by sunspots to a much more complex and frankly more elegant model. It's a three-part system where sunspots are just one piece of a much larger global dance. So why does all this matter? Well, this new three-part model gives us vital new data for the computer models we use to understand the sun's magnetic engine, the solar dynamo. And better models mean better predictions about how strong future solar cycles will be. And that has very real-world consequences for our satellites, our power grids, and all sorts of technology here on Earth. You know, what's so cool about this is that the discovery wasn't made by looking at the biggest, brightest, most obvious things on the sun. It was made by cleverly removing them to see what was hidden in the quiet underneath. And it just makes you wonder, right? By looking for what's left behind, what other incredible secrets is the sun just waiting for us to uncover?